In this lecture, we're going to talk about the branch prediction. There will be several other lectures on the specifics of different branch predictors. The goal of this lecture is to start with the basic information about branch prediction. To motivate the needed for branch prediction, we're going to start by observing that in general, in the execution of a program in a processor, we have that every 5 to 7 instructions is a branch. So in this illustration, the instructions in gray are not branches, and the instructions in orange are branches. And it tries to give a graphic information of how often we are executing branches when we are executing a program. What is the cost of not predicting or mispredicting a branch? If we have architectures with deep pipelines and with many functional units, the cost is very high. For example, in the AMD Zen 4 is an architecture from around 2022. The pipeline for execution of instructions has 19 stages. So the branch will take many cycles to be executed. If we look at the more recent AMD Zen 5 architecture, it does not make sense to talk about the total number of stages in the pipeline anymore because of the way that these architectures are designed. But if you look at the optimization guide for the AMD Zen 5 architecture, it will going to state that the branch misprediction penalty can be between 12 to 18 cycles, and the typical is 15 cycles. And later, when we are discussing other types of branch prediction, we're going to see that some branches can have a high penalty. So what's the anatomy of any predictor is that we start with the program execution where we are observing the events that we may want to predict. That's valid for all predictors. The execution of the program may contain some predictive information that we're going to use to make our prediction. And then we have to select which events we are predicting. So are we predicting only the branches, or we are making predictions for all the instructions that we observe during the execution of the program? Next, we need to index a predictor. And to index the predictor, for example, we can use the program counter where this is for a local predictor where we are making the prediction for a single branch based on the branch. We can have a global history that's a global predictor, and we'll talk more about the global history, but it's basically the history of the most recent outcomes of the branch that got executed before the branch that we are predicting. We can have also a local history, that's the history of the current branch, and we could use that to index the predictor. Next, we have the prediction mechanism. The prediction may be static or maybe using saturating counters to make the prediction. I can have Markov predictors. And then once I find out whether this prediction was correct or not correct, I may want to provide feedback to the predictor so that it does better the next time. So I take the branch outcome and I change what the values in the predictor are so that the next time that I see this branch, I will take into consideration the outcome of the current execution of the branch. And I'll be updating when I update the prediction mechanism, I may also be updating the indexing of the table where I keep my predictors. So next time I may select a different predictor than the predictor that I selected for this current execution of the branch. And I may also be updating the history or the prediction mechanism if I'm using different types of history, or I may be updating the Markov predictor, for example. So this is the anatomy of a branch predictor, and we're going to start with the observation of the events during the program execution. The event source for the prediction is the execution of the program, and the predictive information that I will use can be encoded in the instruction code itself. So I could, for example, contemplate a situation where the compiler does some analysis and then annotates the instructions. So assuming that I have at least one bit in the instruction code, the compiler could be giving hints to the hardware about the prediction. I could also store the prediction in the instruction cache, which means that during the execution of a branch, I decide which direction that branch went, and then I record that value in a special bit in the instruction cache. So next time that I fetch this instruction, I also fetch the predictive information. So this is how I would be encoding the prediction in the instruction code. Could, as I said, could be a bit indicating the most likely outcome. Could be the information simply that the branch is forward or backward. That information can easily be extracted from the instruction code as well. Or I can obtain the information from some kind of profile information that most likely would involve the compiler as well. Next, I need to select the branch that I'm going to predict. So the question is, when should I be doing a prediction? And a simple solution is to compute, and this is a solution that is adopted by most of the current architectures, is that I'll compute a prediction for every instruction that I fetch, even the instructions that are not branches. And the idea here is that I compute the prediction, but later I decide whether I need to use the prediction or not. I'm only going to use the prediction if the instruction that I have fetched was a branch. Next, I need to index my predictor. So for indexing the predictor, I can use parts of the program counter to index the prediction tables. In this case, I will be only using the history of the outcomes of the previous branches at this program counter. So I do not see the global history. I only see the local history, that is, how did this branch perform, or how did this branch go in the previous execution of this branch. I can also use the history of execution path leading to this program counter. And you can imagine if I get to a branch from different paths, the outcome of that branch may change. So what's the prediction mechanism? The prediction mechanism can be static. For example, I can say that if the branch is a forward branch, I will assume that the branch is always not taken. And if the branch is a backward branch, that are the typical branches that I find in the end of a loop, then the branch will be always taken. And the prediction can also be dynamic. For a dynamic prediction, I can use, for example, a finite state machine predictor that will have saturating counters. We're going to look at this design in more details in the next few slides. And I can have a Markov predictor that will be based on correlations. And then for the feedback and recovery, I can use the real outcome to reinforce the predictor. And I must also recover from misprediction. That's part of the recovery mechanism. So if I make a prediction, the prediction is incorrect, I'm going to start speculatively executing instructions that should not have been executed. So when I discover that my prediction was incorrect, I need to fix that by doing something that we call squashing instructions, where we transform the instructions that we start executing speculatively into no-ops. So here I'm going to bring you some observations that were made in the Hot Chips conference in August 2024. Hot Chips is the conference usually happens in Stanford, the University of Stanford in California. And in this conference, all the newest aspects of designs of microprocessors and accelerators, and these days TPUs and other processors are presented. So this is from a talk given by Gerard Williams, who is the Senior Vice President of Engineering for Qualcomm Technology. Gerard has a long history of designing top-end microprocessor. And so this talk should be available online. But at the end of the talk, there's a session of questions and answers. And the observations that I'm going to bring here is from this session of questions and answers at the end of the talk. This talk was presenting the Orion CPU chip from Qualcomm, which was the most recent, most advanced processor from Qualcomm at the time of presentation. So one of the questions that was asked to Jared Williams was, is there a large code set that you need to look at to make branch predictor design decisions? So the idea is when I design a branch predictor, I am running many different programs through a simulator and trying to observe the behavior of those programs to try to understand what should I do with what decisions should I make in my branch predictor. So Gerard's answer is that people have a tendency of selecting, having a bias towards some types of benchmarks, ABC, and he says that what he has learned throughout his career is that it does not matter where it comes from. It can be the Spec 2000, the Spec 2017, can be Deep Bench, Java virtual machines, large programs, server or data center programs. What he says is that what happens is that the properties of these code segments are all useful to design an architecture because they are always giving clues about what we have learned in computing science. Things like data structures, linked lists, pointers, queues, and all these concepts that we are familiar with. They give you all these clues because they are in these programs, and the programs themselves help you study the machine architecture and how to balance it. And then he said, a processor is not just a bunch of transistors, it does come from computing science. So I think that this quote is interesting because it tells you that if you want to be very good at computer architecture, you should also be very good at computing science in general. All the concepts that you learn in computing science in the many different subdisciplines will be important for you to become a good computer architect or a good computer architect designer. And the other thing that Gerard said is that there is 1 in 5 branches in a stream of instructions that generalization, but is of an average. And what he was introducing is the Orion processor, which is a 8 wide machine. So it fetches 8 instructions in every cycle. And then he says that if I wanted to have a sustained instruction per clock of 2 or 3 instructions completing in every clock in an 8 wide machine, you'd like to actually have one branch every 8 instructions. Basically, what he's saying that as a designer, you'd like to be predicting one branch in every cycle. So then there was a question that came through Slack. They also use Slack to receive questions during these presentations, where Daniel Deng says that you have allocated lots of resources for conditional and indirect branch prediction. What is the reason for so many resources? How do you make power performance trade-offs? Gerard, the answer is that you should throw as much resources as you physically can while managing time and power performance at the algorithms for conditional targets and conditional directions to keep the back end of the machine fed. If you don't do this, you are wasting the hardware that you have dedicated to the backend resources. So he's making a claim that in the process of designing a processor, you should really invest lots of time and lots of resources in the branch prediction. Later in this course, we're going to see that the predictors have become quite complex and they use quite a bit of the area of the chip and they use quite a bit of energy as well. He claims that this is a good investment so that we can keep the back end of the machine operating at the best utilization that we can have. Then the next question is, how often does a processor needs to make a branch prediction? Well, from the statistics that we saw already, we can look at control flow statistics. So this is the data that is from 1998. So it is using spec 95 int and using a desktop application. And it says that around 20% of the instructions are control flow instructions, uh, and about 2% of the instructions, 2.5 instructions, are function calls. And about 2% are function returns. And the percentage of conditional branch is between 13 and 15%, with between 40 and 46% of these branches being taken. And the percent of unconditional branches is about 1%, with more than 70% for desktop instructions, more than 90% of these branches being direct. Remember that branches can be also be indirect, in which the destination or the target of the branch can change. So even if the branch is unconditional, it doesn't mean that it's always going to the same place. Indirect branches can go to different places in the program. So a four-way superscalar processor has to predict a branch on average every other cycle, because you're going to have a branch every 5 cycles or so. An eight-way superscalar processor will have to predict more than one branch on average in each cycle of execution. So there is a paper from 2018 that characterizes the SPEC 2017 benchmark suite. So this is a more recent paper than the previous one that we were seeing. And here, what we have in this graph will be the percentage of retired instructions that are branch. So, and there is a number of benchmarks. Those are called the integer benchmarks from the spec suite. And you see that the numbers that show can be as low as 4% for the video compressor X264. But MCF, which is a graph processing an application that computes a path in a graph, it has more than 30% of the instructions that are branches. If you look at the floating point instructions, the floating point benchmarks, you see that the number of branches is lower than the number of integer the branches in integer programs. That's the main difference between integer programs and floating point programs, is that the integer programs have a tendency of having more branches than the floating point programs. The next question is, what is the interbranch distances? That is, how many cycles do you see between branches? This is based on a simulation study for a four-way out of order architecture. And the distances, as you can see, many branches are very close to each other. So we have more than 30% of the branches. The interdistance between them is a single cycle. And you can see this distribution that the number of branches that are at a certain distance reduces as you increase the distance. So 40% of the time there is a 1 or 0 cycle between prediction. So you can say, how can there be a 0 cycle? Well, if you have a four-way architecture, a four-way out of order architecture, you are fetching 4 instructions in each cycle. If 2 of those instructions is a branch, then the interdistance will be 0. Then you can see why the 1 has a high percentage, because if you consider 2 cycles, you look at 8 instructions, and the chance of having at least one branch in 8 instructions is quite high. Remember that the branch resolution takes more or less 10 cycles. In some of the more modern architecture, we are talking more about 18 cycles. So if the prediction is wrong in this four-way architecture, you have up to 40 instructions that are wrong and that are in flight, are being executed by the time that you find out that you made a misprediction. And we're going to see later in other discussions that actually when we combine cache misses with branches, this penalty can be much higher than this for some cases. So next we need to talk about the difference between static branch predictors and dynamic branch predictors. And we're just going to use a few examples to illustrate that. So let's talk about static prediction first. So you have an example of a control flow of a program here in this slide. And you can, so the left side of the slide says that this branch will be predicted as always taken. And this branch will predict it as always not taken. So the dotted arrow indicate the path that you're not predicting, and the bold arrow indicate the path that you're predicting in this case. So a static predictor can make a decision for a given branch, whether it will be always taken or always not taken. And of course, if you make a prediction of always not taken, you can always just keep fetching instructions in the next cycle without knowing the target of the branch that you need to know if you make a prediction that the branch is always taken. So the cheapest, the easiest thing to do is to predict every branch as not taken. So in some early studies, there was indication that about 2/3 of the branches are taken. But when you look more carefully into this study, you see that they were including all the unconditional branches. So 30% of the branches that they are considering were unconditional branches, and of course, they are always taken. So for conditional branches, there does not appear to be a preferred direction. So a conditional branch has about 50% chance of being taken or not being taken if you take all the executions of all the conditional branches into consideration. So there is alternatives for stacked predictors. So one of the alternatives is to predict that a branch that's a forward branch, it means a branch that will jump to a later instruction in the program flow, will always be not taken. And that a branch that's a backward branch, that's a branch that's going back to an execution that has already been executed, will always be taken. So the reasoning for this is that the branch that are in the end of a loop are branches that are backward branch. So the idea is that a branch that is at the end of a loop will always be taken. The reason for the forward being always not taken does not has as a solid ground, but is just based on the style of programming that you observe from programmers. However, it does not take in consideration what the compiler does, because the compiler can generate the branches in different ways, the position of the code. So what was observed based on these benchmarks is that the accuracy improvements are barely noticeable when you use this type of static prediction. And if you do a static prediction based on profiling, which means that you have some information from previous execution of this program, so you have collected basically measuring previous execution of the program in which direction specific branches have gone, and now you're using this information, you get slightly better performance. And of course, as I mentioned, if you do a static branch not taken prediction, you have very little implementation cost on the pipeline because you simply keep fetching the next instruction after any branch. Of course, when that is a misprediction, then you have to squash the instructions that you have fetched speculatively. So for every taken branch, you're gonna have a branch misprediction penalty. Then we have dynamic predictors. The idea of a dynamic predictor is that the prediction for a given branch will change with the execution of the program. So we're not going to make always the same prediction for the same branch. A simple way to do that is to use a finite state machine that will encode the outcome of a few of the recent executions of the branch. There is a more elaborate way to do that, is to not only use the early branch outcomes, but also to consider a correlation with other parts of the program. So it means that you consider the path that you took to that branch, not only the outcome of the branch in previous executions. The next question is when to start the prediction. If you are doing a static prediction, you can start at the instruction decode stage because at that point you know that the instruction is a branch, so you're going to be making the static prediction is a very fast prediction, and you can start at the decode stage. However, if you are doing a dynamic prediction, you are more likely to start the prediction at the instruction fetch stage. Remember that at the instruction fetch stage, you don't know if this instruction is a branch yet. So this means that you're going to calculate a prediction for every instructions, even the ones that are not branches. And later you're going to, of course, only use the result of your calculation for the instructions that are branches. The next question is, what should you be predicting? Uh, First, you need to predict the branch direction. So is this branch taken or not taken? And you need to predict also the branch target. So if you make a prediction that the branch is taken, you also need to predict where this branch will gonna go. And to predict the direction now, the question is where do we find the prediction for the direction? And the next question is how do we encode this prediction? So of course, look at the recent past is always a good idea to make a prediction in general. That's the case for branch prediction as well. So if you have local branch predictors, you're going to be asking what was the direction the last time that the same branch was executed. In a few minutes, you're going to see that you don't only look at the last time, but you look at a few of the previous executions of the branch. In the global predictor, you're going to ask what was the direction the last time that this same history of branches outcome happened. So the idea is that are going to be look at the history, not only of this branch, but also the branch that got executed immediately before this branch. So if I take different paths to get to a branch, I may end up with different predictions. And how to encode the prediction? The prediction can be encoded as a single bit that will say whether the branch should be taken or not taken. And the prediction bit can be set at the prediction time. So when I make the prediction, I recorded what my prediction was in a single bit. I wanted to have hysteresis in my prediction. And the best way to understand the hysteresis is to think about something that we are all very familiar with, especially in the winter. That is the use of the thermostat that we have in our homes and how the thermostat controls the heating system in our homes. So typically what happens is that I set a temperature. In this graph is called the Tconf temperature. I set the temperature that I want my house to be at. And what's going to happen, let's start with on the left of the graph, and let's look at the red arrow. So if my heating system is on and is warming my house, it will gonna get to my comfortable temperature, but it will not gonna turn off the heating system right away. It will keep heating my house until my house is at a higher temperature than the temperature that I want my house to be, and that's called, in this graph, called the high temperature. And at that point, the heating system is turned off. Now the house starts cooling down, and when the house cool down to my comfortable temperature, the heating system does not come back on. It stays off until my house gets to the low temperature that triggers my heating system to come back on. So this cycle is called a hysteresis cycle, and it is used to prevent the control system from being constantly switching on and off. If I were to switch it on when I get to my comfortable temperature and switch it off when I get below my comfortable temperature. We use the same thing for branches. Instead of looking at the last branch only, we look at the last two branch resolutions. And the idea is that I have to make two wrong predictions before I actually change my mind. So to change my prediction. Uh, and the idea is motivated by wrong predictions at the end of inner loops in programs. So we're going to use this 2-bit saturating counter to make our prediction. And with 2 bits, I have 40 states. So I'm going to have a finite state machine that has 40 states. The first state that we are looking at in this slide is the strong taken state. So this means that I have a strong belief that the branch that I'm predicting should be taken. So it means that 2 of the last 3 instances of this branch were taken. So think about a majority vote between the 3 last outcomes of the branch. If the branch is now taken, I remain in the strong state, strong taken state, because it reinforces my belief that this branch should be taken. And then I have a similar state to this, that the strong not taken state. Again, it indicates that 2 of the last 3 instances were not taken. And if this branch is not taken, it reinforces my belief that the branch should not be taken. Then I have the weak taken state. So the TN state. So it's take not taken. So this says that the last instance was not taken, but the previous instance was taken. So how do I get into that state? If I'm in the strong state, where I have a strong belief that the branch should be taken, and the branch is not taken, then I move to the weak taken state. So I still will predict the branch as taken, but my confidence that I should make this prediction is not as high as it was before. If I'm in the weak taken state, if the branch is again not taken, then I have the condition that the 2 previous prediction was not, the 2 previous execution were not taken, and there is one before that was taken. So now I have a strong belief that the branch should not be taken. And I have a similar path, and of course, if I'm in the weak taken state and the branch is taken, I go back to the strong taken state, because now 2 out of 3 of my most recent outcomes are taken. I have a similar path in the finite machine with the weak not taken states. I get the weak not, so this means that the last instance was taken, but the previous one was not taken. So I get the weak taken state by having the branch being taken when I had a strong belief that it should not be taken. And if the branch is not taken when I'm the weak not taken state, I go back to having a strong belief that the branch should not be taken. And if the branch is taken when I'm the weak not taken state, then I have 2 out of 3 outcomes that are taken. So my belief is that this is a strong taken state. So this is how I implement the hysteresis cycle in a branch predictor. Instead of storing only the last outcome of the branch, I have 2 bits that can track the recent history of this branch, and allow notes that if I start with the branch being not taken, I'm gonna have, sorry, if I start with the branch being strong taken, top left of the slide, it will take 2 not taken branches before I change my prediction to the not taken state. So there is just pay attention in your textbook. The description of the strong taken and strong not taken are slightly wrong on the textbook. It's a typo. I can use a 1-bit saturating counter, and basically the goal of this example that we're going to see now is to, in a practical example, to demonstrate the difference between the predictions, the correctness of the prediction for a loop when I have 1-bit or 2-bit saturating counter. So in this loop, I have 2 loops that are nested, one inside of the other. In compiler terminology, we call these nested loops. And so I have some code that gets executed inside the inner loop, the loop J. So I'm not too interested in the code that is execute inside the loop. I'm interested in the control flow for the loops. So I start by testing where m is less or equal than 0. This test is called the guard test when you do compiler code generation. So I decide whether I'm going to ever execute the loop, because if I don't execute the loop, I can just exit. And then I initialize the index variable y to 0. And then I do the same guard test for the inner loop. I see if I ever going to execute this inner loop. And if uh, if I am to execute the loop, then I initialize the index variable j. Now I'm going to execute all the instructions inside the loop. That is the importance of the guard tests. I do not need to do the loop test before executing the first iteration. If I have done the guard tests and I have determined that this loop will execute at least for one iteration. Then I increment the value of j, and then I test whether j is less than n. This is my inner loop, end of loop branch. And then I increment the value of I, and then I test whether I should go back to I. And then I got to the end, and I have the back edge from the test at the end of the outer loop, and the back edge from the test and in the inner loop. What I'm interested here is the prediction of the innermost loop branch, which is that test whether j is less than n. So that branch can be not taken or taken. And this is what will be examined. So let's start by looking, if I have a 1-bit predictor, I can only look at the last outcome of a branch. So let's start the first iteration where I is 0 and j is 0. I do not have a previous execution of this branch, so let's assume that my prediction is not taken. It could have been taken, but let's assume that the initial prediction is not taken. The outcome is taken. So that was a misprediction. Now, when I get to iteration 1, the last outcome was taken, so my prediction will be taken and my outcome will be taken. And as long as I executing this loop, before I get to the end of the loop, for every iteration, I'm going to have the same thing. I'm going to be predicting taken and the outcome will be taken. Then I get to the last iteration of the inner loop. So now I is still 0 and j is equal n. Are you still going to make a prediction of taken because my last outcome was taken, but my outcome will be not taken because I'm getting out of this loop. Next, I get to the iteration 1 of loop I, and the first iteration of loop j in this round, j is equal 0. My last execution of this branch was not taken, so I'm going to predict this branch to be not taken. But of course, this branch will be taken because I'm back at the beginning of the loop j. And then from there on, the predictions are correct until I get to the end of the loop. So if I consider all the executions of loop I in this case, I will have 2 times m misprediction, where m is the number of times that the loop I is executed. Now I will change my predictor to be a 2-bit saturating counter predictor using the finite state machine that we just described. So in my new predictor, again, in the beginning, I will assume that the state of the predictor is weak not taken. That is a reasonable assumption for most of the simulation studies that we do. So I'm in the weak not taken state. The branch is not taken. So the outcome is taken. So that takes me to the strong taken state. So now I'm in the strong taken state, and I'll be predicting the branch as taken, and the outcome will be taken. And as long as I execute in the inner loop, all the predictions will be correct until I get to the last iteration of the inner loop. And now I have that j is equal n. So because I'm the strong taken state, I still predict the branch as taken, but the branch is not taken. So this is a misprediction. This misprediction will make me move to my weak taken state. In the weak taken state, I predicted bench as taken, and now I'm in the first iteration of the second round, the first iteration of loop j of the second round of loop I. And notice that now I made the right prediction because this branch will be taken. And I'll continue to make the right prediction because I go to the strong take state I'll predict as taken, and for the entirety of the loop j in the second iteration of loop I, I'm making the right prediction. So in this case, instead of 2m mispredictions, I have m plus 1 mispredictions, which is much better. Consider that m could be a billion, right? I just saved about 1 billion mispredictions by changing my predictor from being a single bit to be a two-bit saturating counter. And that is the main motivation, the main initial motivation to use multiple bits for the prediction. So we have the saturating counter predictors. The one that we just saw was a 2-bit counter. Then the question is, should we use a 3-bit counter, a 4-bit counter, a 5-bit counter? So how many bits should we use in a saturating counter predictor? So in the accuracy of the branch based on the prediction was studied done in 1993. As you can see, branch prediction is something that has been around for a very long time. And in this study, unconditional branches were included as well, and the predictions are associated with branches after each branch first instruction. So what we have here is that if we have used an average of 26 traces from the IBM 379, the DEC PDP-11, the CDC 6400. Remember, this is a study from 1993. And we're going to consider different strategies with a 0-bit predictor, a 0-bit predictor is a static predictor, a 1-bit and a 2-bit predictor. And we are showing also the average of 32 traces that are run in different types of machine in the MIPS R2000, the SunSpark, the DexVex, and the Motorola 68000. So for 0-bit prediction, we get close to 70% prediction correct. If this is a fixed precision, so what we do here is the first time that the branch is executed, we check its direction, and then every time after that, we predict the branch with the same direction. So we can store, for example, in the instruction cache, what was the direction of the first time the branch was predicted, and use that information. We don't need to have any bits stored specific for the branch. The 1-bit predictor takes this precision to around 90%. And there is a little difference between the big mainframes and the microprocessors. And with the 2-branch prediction, we have a slight increase for the mainframes, and the microprocessors are quite similar to the 1-bit prediction in this study. And then a 3-bit counter yield very minor improvements, and they decide that you should not consider a 3-bit counter. So given a branch, here's a branch in a piece of code. We need to find the current value of the counter used for the prediction. So the question is, how do we find this value? So I have a collection of counters, and I need to find, which of these counters I should use. So what information should we use to index this table? And how we should organize this table? So the first idea is that we're going to create a table with the branch address or a tag that was taken from the address and the prediction. So let's consider first this fairly naive design where I create a tag just like I have tags in the cache. Remember, the tags in the cache are a subset of the bits of the address that I use to access the instruction. In this case, I do not have many entries for the same instruction in this table. Therefore, my tag actually will be the entire branch address. So in this design, I have a number of entries in the table. I'm gonna store the address of the instruction and the state of the predictor in this table. But let's think about this design for a little bit. If I consider I consider 32-bit machine, of course, I don't need the 2 lower bits of the address. So if I consider 32-bit machine, I will have about 2 to the 30 entries in this table if I want to have a place for every branch that can possibly appear. And I'm going to be using more bits for the tag than for the prediction. So I use 30 bits for each one of the tags and only 2 bits for the prediction. That seems quite wasteful in terms of hard storage and in terms of the energy to access all this information. So the solution is to ditch the tags altogether. We're not going to have tags in our prediction tables, which lead us to the design of the pattern history table. What's the idea of the pattern history table is that I have my predictor bits that are my 2 bits stored on the table. And now I'm going to index the table using some bits of the program counter. As you can see in the picture, it indicates that I'm going to use k bits, and those k bits will not going to be the lowest k bits of the PC, because that could end up many branches addressing the same entry in the table. I don't want that. So I'm going to skip the lowest bit and I'm going to use some other range of bits from the PC. And with this design, now I'm flexible. I can decide the size of my predictor table. It will be 2 to the k entries, and I use k bits to address the table. So each entry of the pattern history table, we start the state of the finite state machine that we saw before that's associated with the branch. And I will use some bits from the PC to hash into this table to select which entry of the table I'm going to be using. Of course, there will be aliasing. I can have multiple branches for which those k bits are the same, and those branches will alias and map to the same entry in the table. So later we're going to see some mechanisms to address this aliasing. This aliasing can be unharmful if the 2 branches, for example, have a tendency of going in the same direction. But this aliasing can also be destructive if the branches go in opposite direction. So if I have aliasing, I can have performance degradation because of the aliasing. So this prediction that uses the some bits of the PC to index the predictor and use a 2-bit saturating count, a table of 2-bit saturating counters, is called a bimodal predictor. Try to remember this name. In discussing other branch predictors later, we also going to refer to the bimodal predictor as our baseline predictor. So what's the accuracy of this bimodal predictor based on the PHT? So we are looking at the different sizes of the PHT here, starting with 32 up to 64K. And I wanted to draw your attention that this graph is drawn in such a way to emphasize the difference. So in the y-axis, I'm starting at 88 and going to 98. This is not something that we should in general use to represent information graphically, but this is the way it appears in the original paper and also in our textbook. So this is the conditional branch accuracy, and it's based on 10 spec 89 traces. And what you see is that as you increase the size of the PHT, the accuracy improves up to about 2K. Any PHT that's longer than 2K does not give you much more accuracy after that. There is an alternative to the PHT that is to store, to embed the prediction in the instruction cache. So the idea is that the must update that first of all that I'm gonna store bits on the right side of the cache line. Here I have for this instruction cache that contains 4 instructions, I'm gonna have 4 prediction bits that I'm gonna update every time that I make a prediction. So I will, instead of having a PHT, for example, if I'm basing my, if I have the equivalent of 1-bit PHT, I can store this bit with the cache line. The problem is that I'm gonna have to update this bit about every 4 to 5 instructions that I execute. And if I have a 4-way or 8-way machine, it means that in every cycle of execution, I need to update these bits. But this is a solution that can be used as well. And In terms of where the prediction is stored, it can be embedded in the instruction cache. The Alpha 21264 use the solution. The Sun Ultra Spark use the solution. The AMD K5 use the solution. The MIPS R10000 has a separate PHT. The IBM Power PC 620 has a separate PHT, and the Intel Pentium has a separate PHT. Nowadays, every processor has separate branch prediction tables instead of having it embedded in the cache. So I'm going to stop here this lecture, and the next lecture I'm going to do the second part of the branch prediction discussion.